Have you ever wondered how a factory that's juggling thousands of different custom products actually gets anything done on time? Well, behind the scenes of all that chaos, there's this incredible, high-stakes puzzle being solved every single second. So today, let's dive into the fascinating world of job shop scheduling.
To really get our heads around this, we're not going to start in some giant, overwhelming factory. Nope, we're going to shrink it way down to something a lot more familiar, a busy, custom workshop.
Okay, so picture this. You're the boss, you've got an order for a custom chair, one for a bookshelf, and another for a picture frame. They all need to be cut, sanded, and painted, right? But here's the catch. Each one needs those machines in a totally different order. How in the world do you organize that workflow? Which job gets to use this saw first? That question, that's the core challenge we're tackling. And that, right there, is the official name for our workshop's little dilemma, the job shop scheduling problem. It's all about trying to coordinate a bunch of unique jobs, each with its own special recipe of tasks and machines, to create one perfectly efficient timeline.
Now, what makes this a real puzzle isn't just the number of jobs you're juggling. It's the super strict set of rules you absolutely have to play by. And believe me, these rules are non-negotiable, and they're what make finding a solution so incredibly tricky.
So these rules might look simple, but they are ridiculously restrictive. First up, fixed routing. This means you have to cut the wood before you sand it. The recipe is set in stone. You can't change it. Second, one at a time. Your table saw can't be working on the chair and the bookshelf at the same time. It's one or the other. And finally, no interruptions. Once you start painting that chair, you have to finish the job. You can't just stop halfway through to do something else. These constraints are what make the whole thing so tough to solve.
All right, with those rules locked in, what does it even mean to win at this game? What's the ultimate goal we're all shooting for?
Well, it all boils down to one key idea, the Makespan. And that's just a fancy word for the total time on the clock, from the second your first task begins to the exact moment that very last job is all finished up. The entire game is about one thing, shrinking that Makespan down to be as short as humanly possible.
So, we've got our rules, we've got our goal. Seems pretty straightforward, doesn't it? Well, this is the part where the puzzle goes from just being tricky to being completely, mind-bendingly complex. You see, in the world of computer science, job shop scheduling is what's known as an NP-hard problem. Now, all that really means is that as you start adding more jobs and more machines, the difficulty of finding the one single perfect schedule doesn't just go up, it explodes. We're talking exponentially.
Let me put it this way. Which is 10 jobs and 10 machines, the number of possible schedules you could make is literally greater than the number of atoms in the known universe. Yeah, just let that sink in. That's why you can't just tell a computer, hey, check every option and find the best one. There isn't enough time or computing power in the entire world to do it.
So, if finding the perfect schedule is basically impossible, how does anything get made? How do real-world factories handle this every single day? Well, the answer is, they kinda cheat. Sort of.
They do it by making a really important trade-off. See, on one side, you have what are called exact methods. These will guarantee you find the absolute 100% perfect, shortest Makespan schedule. The problem? They are so painfully slow, they're useless for anything but the tiniest, simplest problems. But on the other side, you've got heuristics. Think of these as clever shortcuts or rules of thumb. They find a very good schedule. Maybe not perfect, but really, really close, and they do it super fast. For just about every industry out there, very good and fast is way better than perfect, but we'll have it for you in a million years.
And this has led to a whole toolbox of these good enough approaches. You've got simple priority rules, like always work on the shortest task first, and then you have much more complex stuff, like genetic algorithms, that actually mimic natural selection to evolve a really efficient schedule. The main point is, people have found a lot of smart ways to get a practical answer to an impossible question.
Okay, so this clearly isn't just some theoretical puzzle for computer scientists to nerd out about. This exact problem and its very practical solutions are actually running the world all around us every single day.
You'll find it in any plant making cars or electronics. It's the absolute heart of production planning for aerospace parts. It's in our little custom workshop, of course, but it even shows up in service industries. Think about it. A patient in a hospital needs a series of specific tests, an MRI, then a blood test, then an X-ray, using different diagnostic machines. That's the same exact puzzle, just with different jobs and machines.
And that brings me to the final, really critical question I want to leave you with. We live in a world that demands everything faster, cheaper, and more personalized, and that's putting an insane amount of pressure on these scheduling puzzles. So as the stakes get higher and the problems get even more complex, how long can we really rely on good enough? And what kind of breakthrough are we going to need to keep our world running on time?